Hello everyone, I'm Rajitha Athukorala, and today I'll be trying to give an overview of my whole PhD project in 10 minutes. So let's see how it goes. So the aim is to come up with a probabilistic model for streamflow prediction in Australia. So the last couple of months, we've been experiencing one end of the spectrum. We had quite a lot of floods, one after the other. So I think I'm at the right place of research. But then again, if you go back a few years, it was very common to hear that our rivers completely run dry. So it's a tale of two extremes. Then my methodology that I'm trying to propose will be data-driven. It will be a probabilistic model, so there will be a quantification of uncertainty. And also it will be able to adapt to varying climate conditions, because we know the nature is always changing, evolving. We cannot stick to one set of parameters or one set of model. And then I will try to make sure that my model will be able to forecast in both space and time, which I will explain here. So ideally, the model that I propose should be able to predict beforehand how much water there's going to be in a certain river at a certain time, as well as it should be able to give me an indication, at least a prediction or an estimate of how much water there will be in a different location where we don't have data. Because Australia is huge, I'm coming from Sri Lanka, the rivers run so long, and sometimes the data that we have, the gauging stations that we have, could be about 20, 30, 50 kilometers apart. So we really don't know what happens in between. There's quite a and then this is a big problem in water counting, because we don't have any estimations or predictions or any observed value. We really don't know what happens to this water. So the way I look at it is that the nature, the system is so complex, but I'm going to try to build up my model step by step by adding complexity. So I'm going to add this complexity in 3 steps. Because of the limited time that I have to finish my PhD in 3 years. So the first or the most fundamental basis would be to come up with a streamflow forecasting, considering this non-stationarity over time. So that is my first step, which I've already completed. And then today I'll try to give an overview of the second step, which I'm halfway through, where I then try to add these 0 observations. So in most of the ecological data sets, we have quite a lot of 0 observation, which is a problem statistical when it comes to statistical modeling. You can always chuck that off and then try to model the nice part. But then again, we believe there's quite a lot of useful information embedded in these zeros. So there's always that. And then the third step would be the fun part, where I try to extend this existing methodology to tackle the non-stationarity over time and space, the spatial stuff. Okay, so the way that I go about is I try to divide the bigger problem into 2 smaller problems. So we have days with 0 flows, we have days with non-zero flows. So I'm gonna make sure that I divide this smaller problem and tackle them separately and have different distributions to represent them. All right, so first off, I check what is the probability of the stream flow being 0. And then I represent that with a point mass at 0 using a direct delta function. And for the non-zero flows, I go with a gamma distribution to represent it. So I can make things more and more complex. I can make a mixture for the non-zero flows. I can use several gamma distributions to represent low flows, medium flows, and high flows. So I can build up on this, but I'm gonna only talk about the very simplest version. And another key point here is that for the non-zero flows, I'm going with the gamma distribution. The shape and rate parameters of this distribution will be parameterized using some set of covariates. So for example, it could be rainfall in the previous day, it could be temperature, it could be soil moisture, it could be any climate variable that drives the system in a particular catchment, and it could change from catchment to catchment. And then, as some of my colleagues were talking about, we might even be able to adapt a
a variable selection method on top of that to make things even more interesting and more feasible. So assuming that conditional on the set of parameters that I chuck into this model and the most adjacent spatiotemporal observation, the covariates xi, that the data are independent, I can write down the likelihood this way, but then I end up with a very long expression for the conditional posterior, which does not have a closed form. So I cannot go with a Gibbs sampling. And right now I'm using adaptive metropolis algorithm for the sampling, which works okay for smaller models. But when I try to add more and more parameters and more complexity, it just cannot handle it. So a very active part of my research is to come up with a Hamiltonian Monte Carlo sampling method. I'm not going to reinvent Hamiltonian Monte Carlo method, but the problem here is that there is a very hard constraint. So when I'm searching through this n-dimensional space, let's say the solution, in my model, because I'm using a gamma, there is a brick. There's like a very hard constraint, which the sampling sometimes tends to work very poorly. So because of the Hamiltonian Monte Carlo sampling requires gradient calculation, I need some incentive to use it. There should be some way to utilize it in such a way that it is more feasible than at least the adaptive metropolis, which is like the most simpler random walk. So that is part of my active research on that front. But then again, I try to use the model that I'm trying to propose for the Australian context. I selected this Avoca River in Victoria. And then I later found out that this particular river that I randomly chose has the most variable flow pattern out of all the Victorian rivers in the Murray-Darling Basin. So well done. So I thought maybe if I can do a good job with my simple model for this data set, maybe it could be a good step to start off and say, okay, maybe it works. So as expected, within sample predictions are pretty good. Out of sample, it's doing okay, I'd say. But then again, as simple as it sounds to you guys, that the prediction of zero flows, it sounds so simple. Even for me, intuitively, I thought that should be pretty straightforward. But actually, in my model, that seemed to be the most hardest problem to tackle. I'll show you this plot. So what I have plotted here is the rainfall received in that particular catchment that I used in red rock plot, which is some of the days that my model is saying that there's going to be water in the river, but actually there is no water. So that's a wrong prediction. But if you can see how much rainfall there has been in that particular set of days, you can see there's some days with more than 20 millimeters of rainfall, but still the catchment is not producing water. So that makes the problem even more interesting statistically, because it makes me wonder what can I do to make things more complex and try to find these hidden processes that happens in the nature. So the way forward is, number one, try to come up with the efficient sampling, because ideally I want to make sure that I can upscale this methodology. And then maybe another variable selection on top of the model to make things easier, try to select the best set of covariates. And then again, as I said, I can make things more and more complex, but then again, have to keep it parsimonious as well. So the way that I think I can deal with that is to add more mixtures to the non-zero flows, try to characterize low flows, medium flows, and high flows. So these are some of my references. So thank you for listening. And if you have any questions, I'll be here.